Okay, welcome everyone to the first lecture after lunch on the last day, and I want to begin by thanking the organizers first and all of you for, them for organizing the conference and all of you for coming and participating in the activities. As usual, if you have any questions, feel free to interrupt. I said I will talk about the classification of the rough subjective classification of partition identities. I will come back to that, but the main topic I want to talk about today is construction of some evidently positive partition generating functions. And I'll try to give you some main ideas, and I'll sweep the proofs under the rug. And they are technical, not very difficult. Once you see the combinatorial picture, then the proofs follow after that, because almost in all combinatorics, the point is to see or not to see. Now, let's start with a partition into distinct parts. Let's take a partition into distinct parts. Four, 7, 9, and there's a reason why I'm writing them in reverse order. 13 and 18. I want to decompose this partition into distinct parts, a base partition or a minimal partition, and an unrestricted partition. Into a partition into unrestricted parts and a base partition or a minimal partition. Both Ali and Joanne showed you how to do this using Ferrer's boards, but we are going to follow a different route today. We will place these guys on the real line where they belong. Of course, we are working on integer partitions, therefore we don't care what happens on the negative side. So 0 is here, 1 is here, bear with me, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So we have an 18 guy here. That's going to be a part. I wish I had my magnets with me, but I forgot them in my office. Next we have a 13 guy, yes? 18, 17, 16, 15, 14, 13. Very good. What else? We have a 9. 9 is here. 12, 11, 10, 9. That's another part. And a 7. And a 4. 6, 5, 4. Yes. So basically, this is the reason why I write partitions contradicting all other speakers in the reverse order, in the non-decreasing order. I want to start with the smallest part. What we're going to do is we want to keep the condition, we want to keep the distinctness condition, and we want to make these guys as small as possible without violating any conditions. So we will make them basically walk on this real line. What can we do for 4? Well, 4 can hop back 3 units, yes? 1, 2, 3. So 4 walks back to 1. There is no 4 anymore here, it becomes a 1. And we record the number of steps we took. We took 3 steps there. We do the same for number 7. We can make it walk all the way back to 1. No, not 1. Why not? Because we want to preserve the distinctness condition. Therefore, we can make it walk back all the way back to 2. We don't have a 7 anymore. And how many steps did we take? 5 steps. And do the same for the rest. 9 comes back to 3. How many steps did we take? We took 6 steps. And next in line is that 13. 13 comes back to 4. And we will have taken 9 steps. And then finally, 18 goes back to 1, 2, 3, 4, 5. Steps. It's obvious that these number of steps are in the desired order, and this is going to give us the partition we are looking for. This is going to be the partition into unrestricted parts. And those guys over there, they are going to give us the base partition or the minimal partition. If you tell me the number of parts you want, I can tell you the minimal partition into distinct parts having that many parts. In fact, this identification, this decomposition tells us immediately that if we classify according to the number of parts, the series and running from 0 to infinity, Q to the weight of the base partition divided by the unrestricted partition into at most n parts, because maybe we don't move any parts. So we have to allow some zeros there. Q sub n. And what's going to be the weight of the base partition, 1 plus 2 plus 3 up to n. This is going to be n plus 1 choose 2. This is the generating function for partitions into distinct parts. So this was our toy example. This was known 200 years ago, maybe. Any questions here? If you look carefully, you will have noticed that 18, 13, 9, 7, and 4, this also satisfies the Rogers-Ramanujan condition. So the above partition also satisfies the Rogers-Ramanujan difference conditions. So we can decompose that into a minimal partition or a base partition satisfying Rogers-Ramanujan conditions, and again, an unrestricted partition. We'll play the same game again. Which parts do we have? We have 4, starting from the smallest, 4, 7, 9, 13, 18. So 4 will come back to 1, yes? Again, 3 steps. We cannot make 7 go back to 2 anymore, because if we place a 2 next to 1, this won't satisfy the Rogers-Ramanujan condition anymore. The smallest 7 can go is 3. We don't have a 7 anymore. And how many steps did we take? We took 4 steps. And for similar reasons, 9 will not go back to 4, but it's going to go back to 5. Registering 4 steps. And 13 will go back to 7. In how many steps? In 6 steps. Is it? Yes, 6 steps. And finally, 18 goes back to 8. No, it doesn't. It goes back to 9. Taking 9 steps. So this time, this is going to be our unrestricted partition. And this guy is the minimal partition, the partition into smallest number of parts satisfying Rogers-Ramanujan condition. Rogers-Ramanujan 1, to be exact. The base partition. Therefore, we can immediately write the sum n running from 0 to infinity, q to the weight of the base partition divided by the generating function for unrestricted partition up to n parts. Yes, at most n parts. Q sub n, and what's that weight over there? 1 plus 3 plus 5 plus 7 plus 9. In general, it's going to be n squared. So this is the series side of the Rogers-Ramanujan. Happy so far? Any questions? This was in Schur's version of Rogers-Ramanujan identities. Now, after Rogers-Ramanujan, we will fast forward a few decades, and we will talk about Gordon's theorem. To write Gordon's theorem, we will switch our notation, and I'll follow Walter's notation for the frequency of parts in partitions. So for any partition lambda, xk will be the number of appearances of k as a part in lambda. Or we partitionists call this f. F sub k, f for frequency. Of course, x is a more handsome letter, I'll give you that, but we just call it f sub k. Anyway, in this notation, Rogers-Ramanujan identities become the following. In particular, Rogers-Ramanujan 1 becomes the following. Number of partitions of n, again, for any non-negative number n, number of partitions of n satisfying fi plus 1. Strict less than 2 equals the number of partitions satisfying some congruence condition. Let's write the congruence condition as well. F of 5j equals f of 5j plus 2 equals f of 5j plus 3 equals 0 for all j. So we don't have any multiples of 5, 2 more than multiples of 5, 3 more than multiples of 5, so we are left with residue classes 1 or 4 modulo 5. So this is the Rogers-Ramanujan identities. What Gordon did is to let this number be bigger. So the combined frequencies of consecutive parts can be as large as you want up to a certain point. So Rogers-Ramanujan-Gordon theorem asserts that number of partitions into parts satisfying the combined frequencies of consecutive parts for any consecutive pair is strictly less than k, where k is greater than or equal to 2, equals the number of partitions of n into parts which are not congruent to 2k plus 1 or 0 modulo 2k plus 1, k modulo 2k plus 1, and k plus 1 modulo 2k plus 1. Equals 0. It's really easy to write generating functions, infinite product generating functions for the right-hand sides. We are not going to do that. Easy to write infinite product generating functions. But we will focus on the left-hand sides, the multiplicity conditions, if you want. By the way, Gordon's theorem was independently discovered by Gordon and Andrews back in the 60s, and Gordon ran to the typewriter faster. So he published first. So the theorem is called Ramanujan-Gordon identities. In 1974, though, Andrews found the generating function, the evidently positive series generating function for these partition enumerants. So n greater than or equal to 0, number of partitions satisfying that condition, fi plus 1 less than or equal to k, q to n. In fact, he threw in the number of parts as well, but the big deal is the shape of the q series. This is a k minus 1 fold sum, where you call the indices n1, n2 up to n sub k minus 1, all greater than or equal to 0. A very nice form, and this series has since been called Andrews-Gordon type series. So downstairs you have a bunch of q factorials, q sub n1, q sub n2, q sub nk, and upstairs you have a monomial, q raised to a big power, which is big N1 squared, big N2 squared, all the way down to a big Nk plus 1 squared. So what are these big N's? They are the following. You start with a given index, n sub r, and you add your way up to the increasing index side. N sub r plus 1, n sub r plus 2, n sub k minus 1. So this form of series where you have a monomial on top and bunch of q factorials downstairs, this is called an Andrews-Gordon type series. Of course, later people loosen the conditions. I'll tell you what losing the conditions mean later. But for now, for us, this is the Andrews-Gordon type series. And this series equaling the infinite product generating functions, that's the companion to the Ramanujan-Gordon theorem, and that one is called the Q series identities, is called Andrews-Gordon identities. Multiple series look a little less understandable than the Ramanujan series, because we could interpret the Ramanujan series right away. We could write the generating function for partitions into distinct parts, but if we want a combinatorial interpretation, this series doesn't lend us any hints. It was Bressoux who first combinatorially constructed this series, and he did it in 1981. Because Andrews showed that this series, together with some x's, x1 through xk minus 1. Sorry about that. So Bressoux, in 1981, gave a combinatorial interpretation, or a combinatorial construction. And I'm going to sketch you an alternative combinatorial construction of these series. Okay. Now, we will start by writing a base partition here. So I feel like having some ones. 1, 1. How far up can I go? Well, given this condition, I can go up to k minus 1. So we can have k minus 1 ones. But because we used up all our credit, we cannot write any 2's. Yes? So we have to leave the 2 column empty. But we are free to write any number of 3's. Right? Well, not any number of 3's, but again, we can go up to k minus 1. Once we use up all k minus 1 slots there, we cannot write any 4's, but then we can have bunch of 5's, bunch of 7's, bunch of 9's, and so on. At some point, we feel like reducing k minus 1 to k minus 2, reducing that k minus 2 to k minus 3 on the way, all the way down to 1. Basically, if you look at this shape from very, very far, you will see this staircase. And you call the number of the towers of k minus 1 numbers stacked on top of each other, you call that number n1, towers or stacks. The next batch, and 2 stacks. The next batch, and 3 stacks, and these are exactly the indices you see over there. Any questions so far? And then if you want to calculate the weight of this base partition, you look at the first story, the entry level, the entrance level. You have to go all the way up to 1, 3, 5, the odd numbers. How many of them? N1 plus, N2 plus, N3 plus, N4. That many odd numbers. That many distinct odd numbers. What do they add up to? Big N1 squared, because we have little n1, little n2, little n3, and so on. If you do it for the second story, you stop at n2. Why? Because the last one had only singletons here. And that's going to give you the sum for the second level, sum for the third level, and so on. But what about the denominators? By the way, any questions about the base partition there? Does it make some sense? Okay. How do we move these things about? Take a stack of k numbers, start with 1. Or let's start with a stack of 4 numbers. If we want to move this forward, what's the walking sticks a clown has? What's the name of those walking sticks? Anyway, you see the picture, a clown walking on long sticks. Stills. Can you picture him moving? Yeah. Picture these guys moving the same way. So they can reach 2, but only after 4 steps. Because we don't want to make them too far apart, otherwise they're gonna fall. Make some sense? That's the whole idea. This is how we move stacks. Of course, once you grasp this idea, then you need to work out the details, because what happens if 2 of them come close to each other? What happens if a taller one encounters a shorter one? What happens vice versa, so on and so forth. I'll give you a small example for that one as well. Suppose you have a stack of 3 guys here, and 3, 4, 5. Yes. There are lots of details I'm leaving out, but I'm trying to give you the core of the ideas. And I want to make these guys walk. Okay? The first move is simple. We just move the top one into being a 2. This is the first step. The second step is, again, not very difficult. The second one will be made into a 2. But then we don't want numbers on the same level to come too close to each other, so we refrain from moving this one. Next move is going to be, okay, try moving this 2. It's not going to work because it's going to come too close to the 4, but the top one is free to move. One more step, again, we cannot move this one, we cannot move that one. We cannot move this 3. We will move that one. And this will become, again, we are trying to move the stack of these 3 guys. If we move this 4, then the middle will be too far ahead, and the clown will look like this. And you don't want that to happen. Therefore, we are moving the top 4. Okay, let me box things so we have a clearer picture of which part moved. Just follow the arrows. And the last example of the move I'm going to give you is 1, 2, 3, 5, 5, 5. So in how many moves? 1, 2, 3, 4, 5. In 6 moves, the stack of 1s pass through stacks of pass through shorter stacks, and then it can continue its way. Make some sense? That's the whole idea behind constructing the series side of Andrews-Gordon identities, and this is my PhD thesis in a nutshell. Of course, I mean, you need to prove uniqueness, and this correspondence being one-to-one and onto you can explain everything. No 2 partitions fall into the same bunch of partitions and in the same base partition, but that's the general idea. Once you have this picture, the rest of the proof is mechanical. You prove this won't happen, this will happen, so on and so forth. Any questions? Okay. The funny thing is, this is equivalent to Bressu's construction. And nobody, including myself, proved that yet. But it's going to be tedious because Bressu uses recursion or induction, if you want to call it that way. And I mean, the details will be very messy, very technical, so nobody undertook the project yet. And I don't plan to do it anytime soon. We just believe they are the same. But again, ladies and gentlemen, this is the combinatorial construction of series side of Andrews-Gordon identities. And this give us a clue about evidently positive generating functions, because this is an evidently positive series. If we can determine a base partition in some way, And if we can define a bunch of combinatorial moves, then you have the form of the series right away. Because the weight of the base partition will be the numerator power of Q, the exponent of Q, and downstairs will be the moves accounted for by various partitions. And they are most of the time Q factorials, and you have Andrews-Gordon type series. We can do this for Caparelli's identities. And this is proven by Kanada and Russell and myself independently. But Matthew Russell maintains that this doesn't belong to any of us. This series belongs to Dus and Lovejoy. Did you write this before?
Dus and who?
Yes? Dus and Lovejoy.
Ah, and Lovejoy. We wrote, yes, we did.
You wrote these series?
We wrote this series, yes.
Ah, okay, okay. So forget about us. So this belongs to Dus and Lovejoy.
I think it was 2017 for us.
17?
But maybe you were before, I don't know.
Okay. So the series is Q to 6m squared plus 6m times n. I will figure out these coefficients in a minute. Plus n squared, 2n squared, 2n squared, yes? Divided by q cubed m, n, where m and n are greater than or equal to 0, equals an infinite product. We are talking about this series, right?
And for us it was the weighted verse version, but if you do some dilation, you get that.
Okay, okay. So basically, yeah, I mean, they did the undilated version, but neither my construction nor Kanada and Russell construction, they don't come from weighted words. Okay. If you remember the multiplicity side of Caparelli's identities, the multiplicity side was given a partition lambda, I'll write it in the conventional notation, number of partitions of n, lambda equals lambda 1 plus lambda 2 plus lambda 3, lambda 1 being the largest, and it's non-increasing. Lambda I minus lambda I plus 1 is greater than or equal to 2 and greater than or equal to 4 unless the sum of these guys equals a multiple of 3. And I think we don't allow any ones here. If you think hard enough, you will be convinced that this is equivalent to the description Joanne gave you before lunch. This is the multiplicity side. And, okay, let's see if we can hit difference exactly 2 and exactly 3. In which cases can we hit difference 2 and difference 3? Let's experiment a little. For instance, after 2, can I write a 4? can I have this piece of partition somewhere? Well, 2 and 4 add up to 6. That's a multiple of 3, so this is allowed. How about 2 and 5? 2 and 5 is not allowed because 2 and 5 don't add up to a multiple of 3. So this is not allowed. 2 and 6, it is allowed because the difference may be greater than or equal to 4, and in fact anything greater than 6 is allowed. So this is okay, that is not okay. 2 and anything greater than 6 is okay. I'm not going to circle them for a reason I'll tell you in a minute. How about 3 and 5? Not good. They are too close together and they don't add up to a multiple of 3. But 3 and 6 is okay. The difference is less than 4. The difference is 3, but they add up to a multiple of 3. And again, 3 and anything greater than 7, these are allowed. If we begin with 4, we cannot have 4 and 6. Can we have 4 and 7? We cannot have 4 and 7 either. But 4 and anything greater than 8, we can have these as subpartitions. In general, 3k minus 1 and 3k plus 1, these two numbers can come too close together because they add up to a multiple of 3, and 3k plus 3 is also okay. These are the only two instances where we can have difference exactly 2 and exactly 3. So we call these pairs. Given a partition satisfying comparability condition, and call everything else a singleton. I want to keep that. I want to keep this. So I'll define you the moves first. I'm not going to write things at different levels. The pair 2, 4 will move forward as 3, 3. And this will move forward as Did I forget my own stuff? Five and 7, yes. So every time we make the weight of this pair 3 more. Is that right? 6, 9, no? Oh. This is 3 and 6. Yes, sorry about that. That's 3 and 6. Repetition is not allowed. So 2 and 4, 3 and 6, 5 and 7. Okay, we are good. We are good. So 6, 9, 12. And if we went on, this is going to be 6, 9, and so on. So this is how pairs move. And if you have a singleton somewhere, let's say 14, this moves as usual. 15, 16, 17. This is how singletons move. And this generating function captures that you have exactly m pairs and singletons. Pairs move 3 by 3, singletons move 1 by 1. And what about upstairs? To get upstairs, you have to write a minimal partition, having m pairs and n singletons that trail them, or that follow them, depending on which direction you look at the partition. We start with 2, 4, but we cannot follow this with a 3 and 6. We cannot follow it with a 5 and 7 either. How about 6 and 9? That's no good. We have to follow it by not 5 and 7, not 6 and 9. We have to follow it by 8 and 10. Yes. And then look at the first element. Increase it by 6. 14, 16. 6m minus 4, 6m minus 2, they are going to be the pairs. You cannot move them anymore backward. This is the tightest configuration, the smallest configuration you can have. After 6m minus 2, you can continue with 6m plus 2, 6m plus 6. Line them up at a safe distance so that you don't create any any new pairs. So you want difference 4 between them and write exactly 4 singletons, n singletons here. 6m plus 4 and minus 2. And then if you take the sum of all those numbers, you will get the exponent of q. Again, there are lots of things I swept under the rug, but this is the general idea. You have to describe what happens when a moving pair comes too close with a singleton. You have to describe some adjustment there, but believe me, everything works out, and this is the construction for parallel identities. I think I don't have time for any more constructions, but I can tell you that a very similar construction works for the first four conjectures of Canada and Russell. For Canada-Russell conjectures, I1 through I4, their very first paper in experimental mathematics. And if you do some more work, if you make connections to Andrews-Gordon identities with some more work, we can evident the positive series for Canada-Russell conjectures I5 through I9, I think. How many conjectures did they have originally? 7, 8, 6?
6, then extended 4.
Okay, I5 and I6. But I mean, the construction is so involved and there are so many details that one of the referees wrote enough already when I sent this paper. But the basic ideas are along these lines. Unfortunately, we couldn't make anything work for the second batch of Canada-Russell conjectures that was joint work with Halime and Balka for PhD thesis. We could get a polynomial with positive coefficients upstairs and q factorials downstairs, but we couldn't boil it down to a single term, a monomial on top. All right. Okay, thank you for your attention. I will stop here.